So electron density is not very high, it's spread out. So the negative charge, doesn't polarize the molecule, doesn't push the electron enough. So you need a catalyst. And then the positive bromine comes in and takes away electrons from the pi electron cloud, which becomes positively charged. And the H then is forced to lose an electron to the benzene electron cloud. So H leaves, forming HBr. And we did the electrophilic nitration of benzene, which is kind of the same, that an NO2 plus electrophile is created. And that does the same thing. It comes along, borrows an electron from the benzene electron cloud. The electron cloud becomes electron deficient because NO2 over here has taken its electrons. And this NO2, the H then is forced to give its electron back. And it joins HSO4-1 to form H2SO4 back again. So those were electrophilic substitution reactions. And then we started talking about these derivative compounds, that benzene has many derivative compounds. You got arenes, which are carbon chains attached, phenols, phenylamine, chlorobenzene, etc. And we talked about these groups. This is taken from the data booklet. So you would always be told which ones are, and we started talking about the 2,4,6 directing groups, which basically meant that once a group is attached, the benzene electron density is not evenly distributed. Previously, it was evenly distributed, but for example, you've got an OH, then the problem is that the O has lone pairs, and those lone pairs, they mix with the benzene electron cloud, and the density increases at this point on carbon's position number 2 and position number 6. And all the other electrons, they get pushed away, and the electron density increases at position number 4 as well. So this is known as 2,4,6 directing groups or 2,4 directing groups. So the electrophile will now be attracted to very specific positions, because the electron density is higher at position number 2 or 6, and it's higher at position number 4. So these were also known as activating groups, because they would push electrons onto the benzene electron cloud. So the electron density would increase. If it's increasing, then the electrophile would be more strongly attracted. So I told you that these were the 4 electron donating groups or 2,4 directing groups. The OH and the NH2 had very large electron donating effect. The lone pairs would overlap with benzene electron cloud very strongly, because you've got spare electrons, so the spare electrons would overlap, and the electron density on this side would increase a lot. So the reactions would be very fast. Alkyl chains, they do have electron donating effect, but the effect is not that strong. They do push the electron density, but carbon chains don't have lone pairs. They don't have lone pairs. They don't have extra spare electrons that they can throw on the other group that's attached to them. So the alkyl chains has a very slight electron donating effect. Cl, on the other hand, the lone pairs, they overlap. It does have an electron donating effect, but at the same time, Cl is very electronegative as well. So it has an electron withdrawing effect at the same time as well. So the net result is that the electron donating effect of Cl would be very less. It's going to push the electrons slightly because it's got too many spare electrons. They will mix with the benzene electron cloud, but not that much, because Cl is overall very electronegative. So it's not going to let go of those electrons. It's not going to throw them or dump them onto the benzene electron cloud, because Cl attracts electrons. So which is why the electron donating effect over here would also be very slight. So the benzene ring is going to be considered activated, and you're going to get faster electrophilic substitution reactions. Yeah, yes, clear. Is this clear up to this point, everyone? Lubena, is this clear? Everyone else? Zoha, clear?
Yes, sir.
Yeah.
Yes, sir.
Achha, so we started talking about the same thing, electrophilic substitution, right? But now we started talking about the electrophilic substitution of benzene derivative compounds. And the first one was arenes. I told you the arenes, they kind of have the same conditions as benzene, nothing different, except for the bromine getting attached at position number 2 or at position number 4. The electrophile will have it's going to get attached to very specific positions, not 3 and 5. To get 2 and 4 or 6. And alkyl chains have very slight electron donating effect. So the reaction would just be very slightly faster, not so the reaction conditions, etc. You still need a catalyst, and so pretty much it's the same reaction except for the 2,4 directing effect. That's it. So arenes and benzene, kind of similar. And then we started talking about phenols and phenylamine. I told you that phenols, they've got a vigorous and a much faster reaction, electrophilic substitution reaction. I mean, instead of vigorous, I shouldn't use the term vigorous. Just that it's got more electron donating effect, which we should write down. Because they're going to ask you why is the reaction faster. So you're going to state that the lone pairs. So the lone pairs, they overlap with benzene's pi electron cloud. And this is the exact explanation you're going to give. With benzene's pi electron cloud. So increasing electron density significantly. Density significantly. So there's going to be a significant increase in electron density, which is why the reactions are going to be very, very fast, because if this bromine and there's no catalyst is needed, there's no catalyst whatsoever needed. Previously, you needed a catalyst because bromine wasn't getting polarized. But now, because the electron density is so high that the electron density over here is pretty high on these positions, that if a bromine molecule comes in, that electron density is sufficient enough to polarize it. The lone pairs are going to get, the electrons in the double bond, in the bond over here, are going to be repelled by the negative charge over here. This bromine would become very strongly positive, and this bromine would become very strongly negative. The positive bromine is going to be even more strongly attracted to these electrons. So you don't need someone else, some FeBr3 catalyst from the other end trying to polarize this molecule. You don't need that. You don't need no catalyst is needed for this reaction. Is that also clear? Is this clear? Yeah. Milail, is this clear? Ethan, Sohail, all clear?
Yes, sir.
Yes.
Achha, so no, remember this, no catalyst is needed. It's going to be a fast reaction. And it's going to be so fast that bromine is not going to get attached to just one position. It's going to be, the electron density is so high that there would be multiple bromines that would be getting attached to the benzene electron cloud, because the electron density is really high. So it's going to be attracting a lot of bromines. So all positions are going to get filled up, 2, 4, and 6. So this is 2,4,6 tribromophenol, and it's a white precipitate. That is what it is, and the same goes for phenylamine. This is what we did. Pretty much the same goes for phenylamine. No catalyst is needed. That's kind of the same reaction. The previous one, the importance of the previous one was that it's used as a test for phenols. You test phenols using this. If there's a phenol, you add bromine. The bromine will get decolorized, but on top of that, there's going to be a white precipitate or 2,4,6 tribromophenol that would be produced. Like, it's the same test as alkenes, except alkenes don't produce a white precipitate. This one will produce a white precipitate. So that's the test. So now we're going to talk about the other ones as well. First I'm going to talk about chlorobenzene. So let's start talking about chlorobenzene. Now the problem, there's a problem with chlorobenzene, and that is that their reactions are usually slow. Okay, so electrophilic substitution, if it were to happen, we're not going to discuss them in detail. I'm just going to say that, I mean, there are 2,4 directing groups. So chlorobenzene, electrophilic substitution for chlorobenzene is going to be slow. Is going to be slow, or just slow. That's going to be enough. So no details are required. A lot of times it's not going to happen. It happens with difficulty, and the reason for that is with chlorobenzene. I mean, the reason for that is that chlorine does increase the electron density over here because of the lone pairs, but it has a very high electron withdrawing effect as well. So what it does is, the overall effect is that it kind of withdraws the electrons. I mean, kind of the electrons get withdrawn towards the chlorine more. I mean, because of the lone pairs, there's more negative charge on this side. It's going to be 246 directing, but overall the electron density on the benzene is going to decrease a bit. So it's not going to attract electrophiles that strongly. So chlorobenzenes usually, they've got very slow reactions. So that's all you have to know about chlorobenzene. Is this point clear? The last one about chlorobenzene.
Yes, sir.
Okay, so that's kind of all about chlorobenzene. We can now talk about the other ones, the 3,5 directing groups. Basically, when we talk about 3,5 directing groups, we're not going to go into detail, because just like chlorobenzene, their reactions would be either slow or non-existent. Specifically electrophilic substitution, nitration, or we actually didn't complete the previous one. I've missed a lot actually. Okay, just a second. Let's take this to the other page. We forgot the nitration of phenols and phenylamine. Just a second. So we can take that discussion onto the next page. Forgotten nitration. So let's quickly do nitration of this thing. Now nitration is both for phenols and phenylamine. Previously, nitration was kind of very difficult, but because it's an activated benzene ring, nitration is going to be kind of vigorous and fast. If you remember the previous conditions for nitration, there were lots of things needed for that. The previous conditions for nitration were given over here. I mean, those are your previous conditions for nitration. You needed concentrated nitric acid, you needed concentrated sulfuric acid, and the temperature had to be 55 degrees centigrade. So pretty strong conditions needed, and then the NO2 would get attached. Those conditions were needed because the NO2+1 electrophile had to be created, because benzene didn't have enough polarizing power that it would sort of rip off the NO2+1 and pull it away and attract it and bond with it. The benzene electron cloud wasn't strong enough. So you had to have all these conditions. But now with a very highly negatively charged with high electron density, a benzene ring in phenol, you don't need these conditions. You just need nitric acid, that's it. So for phenols, because of the higher electron density, so nitration of phenols and phenylamine. and phenyl. I said and phenylamine. So here's a phenol. Just a second. Let me. I said, so here's a phenol. It's going to have an OH. So let's say there's this OH. And all I need for nitration to happen is I don't need all those conditions. I don't need the benzene ring would do its job on its own. It wants to react with dilute nitric acid. It's going to do that. The electron density is sufficiently high that it's going to pull the NO2 plus one out of the, it's going to rip it off, take it out, and polarize the molecule on its own. So an NO2 is going to come in and it's going to bond at two positions. Either it's going to be the second position, there's going to be an NO2 getting attached over here, or it's going to be the fourth position, an NO2 group that would get attached. That would get attached over here. So you're going to get either 2 nitrophenol or it's going to be 4 nitrophenol. So two things, no special conditions required. Benzene ring is highly activated. Is this clear?
Yes, sir.
So, and then there's another nitration of phenols, and that is, I mean, this is number 1. So you got another nitration condition, and that one is the second one. Like if you want to nitrate it even more, use concentrated nitric acid. You want more NO2 groups, so change the conditions a bit. Make it more concentrated. So if you make it concentrated, not only would NO2 get attached on the second position, it's going to get attached to the fourth position as well as the sixth position. And that's going to be 2,4,6 trinitrophenol. So you're going to get this molecule. So the reactions are going to be more vigorous, less extreme conditions are needed for the reaction. For phenylamine, everything is going to be exactly the same. So we can just copy paste this, and I'm just going to change everything to phenylamine. So let's just change this to phenylamine. And I'm just going to change this OH to NH2. And that's it. So identical. The phenol and phenylamine, they have identical reactions. So this sums up the nitration of phenol as well. So is this clear? Nitration of phenols.
Yes, sir.
Okay. Just a bit more vigorous. So just a bit more vigorous reaction. That's it. Normal benzenes would be concentrated nitric acid, concentrated sulfuric acid, plus you would need temperature 55 degrees centigrade. Phenol, the benzene ring is very activated, so you get much milder conditions. And that's about it for nitration. So we were discussing coming back to the 3,5 directing groups. Now, these 3,5 directing groups have severe issues with electrophilic substitution. To get 3,5 directing groups. The problem with 3,5 directing groups is that they've got a benzene, but the benzene has an electron withdrawing group now. So it's got an electron withdrawing group like an aldehyde. An aldehyde is going to have an electron withdrawing effect because the carbon is polar, it's partial positive. So I mean it's a polar carbon. This is partial negative, the oxygen is partial negative. And the carbon is slight positive. So you got a slight positive carbon atom. So that kind of indicates that there's going to be an electron withdrawing effect. So electrons are going to be withdrawn from the benzene. So you got all these electrons on the benzene electron cloud, and now they're going to be withdrawn towards this carbon atom. So there's going to be significant electron withdrawing effect. So the opposite is now going to happen, that the electron density on these carbon atoms is going to be lesser now. Why? Because the electron density over here has been withdrawn towards this carbon atom. Is this point clear? This thing?
Yes.
Okay, everyone else, is this clear? Zoha, is this clear? Ethan, Mohammed, is this clear?
Yes,
Yes,
sir.
sir.
So now the opposite is happening. You've got an electron withdrawing group, and because the electrons are getting withdrawn, the overall effect is that electrons are getting withdrawn towards the group that's pulling the electron. So electrons over here would also be slightly, the electron density over here would also be slightly lesser because all the electrons are getting pushed to the other side. So over here, the electron density would be lesser as well. So it's exactly the opposite. In the previous case, you had all those positions where the electron density was higher. Now all those positions, the electron density is actually lesser. So by default, the positions that are now having a higher electron density are positions number 3 and 5. So 3 and 5, they're kind of the same position. So you just call it 3 position. So 3 or 5 positions, they have relatively higher electron density. So they've got relatively higher electron. They've got relatively higher electron density. So 3, 5 positions. And remember, I'm using the word relatively because overall, there's an electron withdrawing effect. Overall, it's an inactive benzene. So it's kind of an inactive benzene because it's got an even lower electron density overall. Because electron density is getting withdrawn. So that means overall, if it's got low electron density, that also indicates that there's going to be less attraction for electrophiles. Okay, my board is hanging up, so. So there's going to be even less attraction for electrophiles. And either the reaction is not going to happen or it's going to be very, very slow. Okay, is this clear?
Yes, sir.
So just remember all these comparisons. You need to sum this up that that you had these 2 types of groups. The conditions even change. All these 3 directing groups, or the 3, 5 directing groups, they've got electron withdrawing effect, and their reactions are either slow or they just don't happen. All the ones which are 2,4 directing are the ones that activate the benzene ring. They increase the electron density at position number 2 and 4 or 6. And the electrophilic substitution happens much faster. The alkyl chains, they don't activate that much, so the conditions are kind of the same as benzene. The Cl has plenty of issues, so the reactions are also pretty slow. But the OH and the NH2s, they've got a very high electron donating effect. They've got a pretty high electron donating effect. So, which is why their reactions are very, very vigorous. Okay. So, so remember all of this. This is electrophilic substitution of benzenes, and we can try and do past paper questions on this. Just electrophilic substitution. Remember nitration and chlorination or bromination. Those are the two reactions that we have discussed. And the other ones as well, alkylation and acylation. So we're going to try and do some past paper questions on this. Just 1 second if I have. I think this one. Benzene and its compounds. So we can try the first one. So this one, I don't know if the first, yeah, this one. So he's saying suggest reagents and conditions for step 1. So now very often you get this reaction. Can anyone guess what step 1 is? You got a carbon chain, it's got hydrogens, and now it's got a Cl. How now? Remember, it's not a reaction of benzene, so it's got nothing to do with what we have studied right now. So how do you get a Cl substituted in one of the hydrogens in the carbon chain? How do you do that? Do you remember the conditions for me? Like you got a Cl over here. Any idea?
Free radical substitution.
Okay, so that is free radical substitution. That's the first reaction that you studied in AS organic. So this one is free radical substitution. It's UV light. You need UV light and you need chlorine. So remember, you've got a normal carbon chain and it's got hydrogens and they're getting substituted. That's free radical substitution. If Cl is substituted in benzene, then that's the one that we just did. So this one would be just free radical substitution, UV light. And then in the next part, now he's saying, how do you convert this one into this one? Now you're getting a Cl in the benzene ring. So for that you need Cl2. And remember, it's an arene. This one is an arene. Arenes have the same conditions as benzene. And the Cl would get attached to either position number 2 or 4. So it's Cl2 plus a catalyst, which would be AlCl3. So it's going to be AlCl3 or FeCl3.
Sir, in the exam, which one do we write? Like, we're supposed to write any one, right? So can we write AlCl3?
Any one of them, AlCl3 or FeCl3.
Oh, okay.
Okay. The reason I'm using both of them because sometimes they're going to talk about AlCl3, sometimes they're going to talk about FeCl3. Okay. So I mean, what I mean is in the question sometimes it would be written FeCl3, sometimes in the question it would be written AlCl3. In the marking scheme, both are acceptable. Acha, this is something that we haven't done yet. Let's do. So this one is. He's saying, how would you distinguish compound C from compound F? F is this one. What's C? This one. Yeah, I just want to do the mechanism reaction. Just forget that at the moment. Probably not going to do this. Just the benzene questions. Needed. What's the reagents and conditions needed to convert benzene into chlorobenzene? That would be Cl2 plus FeCl3, that's it. Or AlCl3. To bromobenzene, that would be Br2 plus FeBr3 or AlBr3. To nitrobenzene, remember it's benzene getting converted, so it's going to be concentrated nitric acid plus concentrated sulfuric acid plus the temperature has to be around 55. So those are the condition reagents and conditions. And he's asking you, the nitration of benzene is a two-step mechanism that can be represented as follows. Identify the cation. So he's talking about nitration. The cation that's produced is NO2 plus 1. And draw the structure of the intermediate. So you're going to draw that. It's going to be the benzene ring would be incomplete now because the NO2 plus 1 is going to come in. And it's going to pull electrons from the benzene. So on that particular carbon atom, the benzene electron cloud would disappear. There was an H that's already bonded to it. And in the next step, the H would be the one that would lose its electron. So you just have to draw the structure of the intermediate. We did that. Okay, this is the mechanism that we studied. And then he's talking about, he's talking about the carboxylic acid nitration. So he wants us to know what's going to happen if you brominate NO2. I mean, this thing. So you need to know, is the bromine going to get attached to what position? If there's an NO2 attached. So you can kind of have a look. NO2 is a 3-position directing group. Okay, so you have to remember that it's an electron withdrawing group. So for this case, it's going to be 3-position. Like you have an NO2 and the bromine will get attached to position number 3. Is this clear?
Yes.
Yes, sir.
I said,
So I have a question. Can I attach to position number 5 as well? Because like
It's-
we're drawing just 3 and 5, right?
it's, I mean, the reason they just call it 3 because it's exactly the same.
Oh, okay, okay.
Okay. So, I mean, that's exactly the same. I said, then you've got, this one is a tricky one. He's chlorinating this. Now, the problem is it's got a 2,4,6 directing group, NH2. Like if you look over here, the NH2 is a 2,4 directing group, and the other one was carboxylic acid. That's an electron withdrawing group. That's going to direct it at position number 3. So now if you've got 2 groups, what happens now in this case? This is going to direct it at position numbers 2 and 4. This one is going to direct it at position numbers 3. Now, where would the chlorine get attached? Now, the thing is that 2,4 positions are with respect to NH2. So what is the second position? It's either this one or the other one on the other side, right? Is that clear? The second position.
Yeah.
The fourth position is this one. There's already something attached to it, so we're not going to disturb the fourth position. So now look at carboxylic acid. Carboxylic acid says that it's going to direct it to the position number 3. So what's position number 3 with respect to carboxylic acid? This is 1, this is 2, and this is 3. So it's coming out to be the same position. Is that clear?
Yes, sir.
So that means, I mean, both of them are suggesting, I mean, their positions are different, but both of them, it turns out they're going to direct it to the same position. NH2 will direct it to position number, I mean, it's chlorine, so this should be Cl. NH2 would direct it to position number 2. Carboxylic acid, on the other hand, will direct it to position number 3, which according to it would be this one. So it's kind of the same thing. Is that clear?
Okay.
So then you have, what type of reaction is reaction number 1? And what type of reaction is this? Benzene Cl coming in. What name is given to it? We just
Chlorination.
it's electrophilic substitution. I mean, it's chlorine getting attached to benzene. I mean, we just did this electrophilic substitution. Okay, this is all. This is all electrophilic substitution. Do you know what the conditions of phenol are? You don't need a catalyst. You just need Cl2. And it has to be aqueous. That's it. No conditions are needed. No catalyst is needed. It's an activated benzene ring. And the Cl is, I mean, the benzene is so activated that there would be multiple Cls getting attached to it. We talked about 3 Cls getting attached to it. He's showing just 2. So that's fine. So the possible reagent would just be Cl2 aqueous. So is this clear?
Yes, sir.
Let's so now remember, this is not phenol. This is an alcohol. Do you remember, if the OH is attached to a benzene, then it's a phenol. So make sure you differentiate. Alcohol is something totally different. This one is phenol. So let's do some more questions, and we're going to talk about more reactions of benzene. We're just focusing on the electrophilic substitution part. Make sure you revise that, okay? So let's continue next time then.
Okay, sir.
Allah Hafiz.
Thank you.
Okay, take care, Allah Hafiz.